Here in the mechanical design department, we've been informed that the cooling system will require a change in order to accommodate a more powerful processor for a high-end field PG model. This change will need to include using VSA to design and validate the GD&T of the cooling plate and its clearance with the processor. To ensure optimal desired performance and minimum cooling fan noise at 6 sigma quality rate. In the assembly sequence, the PCB is first screwed down to the base housing, then 2 blue cooling pads are pasted to the CPU and GPU. And then the cooling plate with the pipes are placed on top of the cooling pads and secured to the standoffs on base housing with 4 spring-loaded screws. In this cross-section, gap between the cooling plate and the CPU needs to be between 0.42 mm and 0.62 mm to accommodate the thicker 1 mm cooling pad required for the new processor. Excessive pressure from smaller gaps could damage the CPU, while larger gaps could reduce cooling effect. Gap between the cooling plate and GPU has similar clearance requirement. All these gaps are controlled by the 4 spring-loaded screws, quickly tightened down manually or automatically with digital screwdriver at preset torques. To set the proper torque value is critical. This VSA model includes assemblies, parts, tolerances, and assembly operations. In VSA simulation, components are first fabricated according to their GD&T and then assembled together. VSA can simulate making thousands or more products to statistically predict assembly-level fit and finish from part and process tolerances. In simulation, you can visualize part and assembly varying due to tolerances and stack-ups. Here you can see the gap between the cooling plate and CPU vary for each build. Now you see the results of building 5,000 laptops. It shows 4.45% out of spec. This is about 95.55% good quality rate, below the required 99.73%. Most of the bad products seem to have larger gaps, which could cause excessive CPU heat and fan noise. Increasing the preset torque of the digital screwdriver may shift the gap down. The contributor report also shows that variability from the process of screwing down the PCB to the base housing accounts for over 65% of the total variation. We need to add additional screw constraints to further stabilize the PCB. These are the original assembly constraints, and these are the additional constraints from the flex assembly operation. For the torque, empirical data shows increasing it to 2.25 Newton-centimeter can press the spring-loaded screws down by 0.12 mm. Let's activate this flex operation and run simulation again. Voila! Now we are down to 0.08% out of spec, or at 99.92% good quality rate. Finally, we have a quiet yet high-performing field PG laptop at 6 sigma quality with nearly no additional manufacturing cost. Well, at least by design. There are still a couple of steps to close out the quality loop. First of all the GD&Ts and VSA need to go into the master model, ballooned and released. Optionally, 2D drawings can be generated. CMM inspection programs can then be generated from the master model, simulated and optimized. The shop floor inspection results will be automatically fetched in real time to populate the quality report templates in Team Center. Engineers can also investigate root causes of build issues in DPV. The entire process forms Siemens model-based quality solution, a true end-to-end quality engineering solution to help with achieving affordable quality.